This final discussion brings the regulatory perspective together around one central message. Safe drilling depends on maintaining well integrity throughout the entire well lifecycle.
And that life cycle matters. Integrity is not limited to drilling. It begins with planning and design, then continues through construction, operation, monitoring, suspension, abandonment, and decommissioning.
The regulatory focus is control. A well must be designed, constructed, operated, and closed in a way that maintains control along the full length of the well for the full life of the well. That means containing formation fluids, preventing unintended pathways, and managing foreseeable risks before they become incidents.
Exactly.
The useful way to read this slide is through four takeaways: design for barriers, verify critical controls, manage environmental risks, and demonstrate compliance through evidence.
The first takeaway is barrier design. Well, integrity starts before the well is drilled. The design must identify credible hazards and establish barriers that prevent loss of containment. Those barriers include pressure management, casing and cement design, well control systems, formation isolation, and environmental controls.
So the well is not designed first with barriers added later.
Correct. Barriers must be integrated from the beginning. If abnormal pressure, lost circulation, swabbing, weak formations, or kick potential are credible hazards, the design must show how those risks will be controlled. For example, mud weight is not just a drilling parameter, it is part of primary well control. Casing and cement are not just construction materials, they are long term isolation barriers.
And the blowout preventer is part of secondary control.
Yes, it is a critical safeguard if primary control is lost. The regulatory point is that each barrier must have a defined purpose, a credible basis, and a clear role in the overall control strategy.
The second takeaway is verification. A barrier that exists only on a drawing provides no assurance. Critical controls need to be tested, inspected, monitored, and maintained. This is where engineering discipline becomes regulatory assurance.
What forms of verification are most important here?
Pressure testing is one. Cement verification is another. Blowout preventer testing, integrity monitoring, inspection records, drilling reports, and well control checks all provide evidence that controls are functioning as intended. The question is not only was the control installed, the stronger question is can it be demonstrated that the control works?
That distinction is central.
It is especially clear in well control. Kick detection depends on observable signs: pit gain, flow with pumps off, changes in pump pressure, improper hole fill during trips, and changes in drilling behavior. But detection alone is not enough. The response must be supported by equipment, procedures, pressure readings, calculations, and personnel discipline.
So, verification gives confidence before, during, and after the operation.
Precisely. It turns a control from an assumption into a demonstrated safeguard.
The third takeaway is environmental risk management. Well, integrity and environmental protection are closely connected. If barriers fail, formation fluids can migrate. If drilling fluids, cuttings, produced water, or other wastes are poorly managed, the operation can create environmental impacts beyond the wellbore.
So, environmental protection is not a separate exercise.
Exactly. It has to be integrated into planning, execution, monitoring, and closure. The regulatory expectation is that risks are identified, assessed, controlled, and reduced so far as reasonably practicable. That connects directly to choices such as mud properties, lost circulation response, casing setting depth, cement placement, waste handling, and monitoring arrangements.
And it links the life cycle stages together.
Yes, a decision made during design can affect drilling safety, operational monitoring, suspension integrity, abandonment quality, and future site condition.
The final takeaway is evidence based compliance. This is the most important regulatory lesson on the slide. Compliance is not demonstrated by saying that good systems exist. It is demonstrated through credible evidence.
Evidence such as engineering calculations.
Yes, engineering calculations, risk assessments, test results, inspection records, drilling reports, monitoring data, incident reports, and records of corrective actions. Those records show whether hazards were understood, whether barriers were selected appropriately, whether controls were verified, and whether deviations were corrected.
That creates a continuous assurance cycle.
Plan, design, construct, operate, monitor, close. At every stage, the same regulatory questions apply. What can fail? What prevents it? How do we know the control works? And what evidence demonstrates that?
That changes the way, well, integrity is understood.
It does. It is not simply about preventing a blowout. It is about controlling risks to people, the environment, assets, and future operations throughout the life of the well.
The four takeaways are direct: design for barriers, verify critical controls, manage environmental risks, and demonstrate compliance through evidence.
Good design establishes the foundation. Effective controls manage the risk. Verification provides confidence. Evidence demonstrates that the well has been managed responsibly.
That is the regulatory mindset: life cycle control, supported by barriers, confirmed by verification, and proven through records.